The other one we're going to talk about today as well is the covalent network solids. So, compared to other solids, ionic solids, metallic solids, covalent network solids, molecular solids are do you think they're softer or harder? Start by comparing them with an ionic solid. What kind of bonds do we have in an ionic solid? Super hard. Okay. Ionic bonds, yes? Are those strong or are they weak? Strong, okay. How about in a metallic solid? What kind of bonds do we have? Metallic bonds. Are those strong or are they weak? Strong. And in a covalent network solid, what kind of bonds do you imagine we have? Covalent. Okay, we'll look at them in more detail in just a minute. We have covalent bonds. And are those strong or are they weak? No. Covalent bonds are Do you guys have your page with all your little intra-forces and intramolecular forces and intramolecular forces? I'm going to see if I can find mine. That would have been in our solutions unit. There we are. There it is. What are ionic bonds like? Ionic bonds are strong. Covalent bonds are strong. Metallic bonds are strong. If it is a bond, other than hydrogen bonds, which aren't really bonds, if it is a bond, it is strong. If it is an intermolecular force, which includes hydrogen bonds, it is weak. Now, ion dipole can get up there, but they're kind of weird, okay? So if we go back to, there we are. So ionic bonds are strong. Metallic bonds are strong. Covalent network bonds are, covalent bonds are strong. So everything is strong, strong, strong. Whereas IMFs are weak. So if we compare, if we compare the other solids, the ionic solids, the metallic solids, the covalent network solids, to these molecular solids, the molecular solids will be softer or harder? Softer. What else could you say about them? Molecular solids will have what? Yeah, lower boiling points. Lower melting point, actually, because they're solids. When they turn into a liquid, they'll have a lower boiling point. They'll have a higher or lower vapor pressure? Higher vapor pressure. Okay, so those are our molecular substances. Now, hopefully you can tell the difference between an ionic solid and a metallic solid and a molecular solid. Are we good with that? We could recognize them from their particles. Okay. The only one... Well, I was going to say, the only one we haven't really looked at a lot is the covalent network. And if we want to do that, we're going to go backwards to page 14. In a covalent network solid, the key is that all of the atoms share electrons with all of their neighbors, which is different because in a molecular solid, you would have a C sharing a bond with an O, sharing electrons with an O, and then the neighboring carbon dioxide would share electrons. But is there any sharing of electrons between the C and the C and the O and the O? No. Okay, so the neighbors do not share electrons. Neighboring molecules do not share electrons with each other. IMFs, 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 IMFs.
Oh, there's no IMF.
There's no IMFs in the covalent network solid. Okay. So in a molecular solid, molecules are joined by, in a molecular solid, molecules are joined by IMFs, not covalent bonds. Now, if we have diamond, here's a covalent bond that attaches one carbon to another. Here's another covalent bond. Here's another covalent bond. Here's another covalent bond. Everybody is attached with covalent bonds. No IMFs. All covalent bonds. And what do we know about covalent bonds? Covalent bonds are strong. What does that tell us about diamond? It's going to be very hard. High melting point, high boiling point. And in fact, they're so very strong that diamond does not leave the solid form until heated to 3,500 degrees Celsius. At that point, it usually vaporizes, so it doesn't actually melt, it just sublimes. Okay? Now let's take a look at a couple of other representations. Let's look at our, do you see our carbons in here? What hybridization is this carbon here? That's sp3. And how about this carbon here? sp3, they're all sp3. Now, sometimes we don't see all the bonds, like because they're kind of in the, like this one's on the outside, so you know there would be another one here, but it looks like there's only 3, but that's just because we're on the edge of the diamond. Yes? Okay. All right. So they're sp3 hybridized. We have those covalent bonds everywhere. Not all the bonds are shown, okay? We can also have silicon dioxide and silicon carbide. So we had one based on carbon, we have one based on silicon, and we have one based on silicon. What do you notice about these? They are all in group 14. So how many valence electrons? 4 valence electrons. Therefore, they form how many bonds? 4 bonds, which allows it to make that network. You can't get a network based on oxygen. Like you can't have oxygen forming oxygen, 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 oxygen. You can have oxygen be part of it, right, in between silicons, but you have to have something that can form lots and lots and lots of bonds in order to get that network effect. Does that make sense? Okay, so there aren't really very many of them. You should know diamond, you should know silicon dioxide, and that's about it. Okay? Now, so covalent networks are very strong, they're very hard due to those strong covalent bonds. Now we have something that's in between. And that thing that is in between is graphite, which is another form of carbon. So diamond was carbon. Graphite is also carbon. And graphite is what is in your pencil. Yes. Okay. Now, if we look at these carbons here, what is the hybridization of that carbon there? sp2. And here we have sp2. And here we have sp2, sp2, sp2. They're all sp2. Now that begs the question, all of these are single bonds. Where's the other bond? Where's the other electron? And what happens is that we get delocalized.
Between the layers?
Yeah. We get a delocalized, unhybridized p electron. You don't need to know the details of that. No one's going to ask you like, oh, is it an unhybridized p orbital? No, no, no. You just need to know that there's some electrons left over, okay? Leftover electrons. And what they will do is they will kind of hover above and below the graphene, almost like pi bonds. Okay, like delocalized pi bonds. So what we've got then is we're going to have intermolecular forces in between the layers. So this is a strong covalent bond here. But right here we have a weak IMF. So each layer is held onto each other layer by IMF. So you see why I said it's kind of like halfway in between? Yeah? And what can happen if we have delocalized electrons? We have delocalized electrons. We have almost like an electron C above and below each layer. Okay, so there's our delocalized electrons. And what do delocalized electrons allow for?
Conductivity.
Conductivity. Conduction of electricity. Can it conduct in all directions?
No.
It can only conduct in that plane. So if you put a positive up here and a negative down here, it would not conduct. But if you put a positive over here and a negative over here, it would conduct. I don't want you to get too worked up about these things, but if it gets mentioned in a question, just don't be scared by it. Okay, but like you're not going to be asked, you know, why does it conduct in only one plane, blah, blah, that's too much. Okay? It just means you should know that instead of being super hard, graphite's going to be quite soft because you have those IMFs in between the layers.
It also conduct heat.
It would probably also conduct heat, but I wouldn't worry about that. I don't think anyone's ever going to ask you that. Each layer of graphite is called graphene. Again, don't worry about that. You've now heard the word, okay? So here is just another picture of it. One layer is graphene. And just in case you come across this word, these are all allotropes of carbon. Allotropes are just different versions of the same element. And by different versions, we mean different structures. So O2 is an allotrope of oxygen. O3 is an allotrope of oxygen. Graphene is a single sheet. If you take a single sheet of graphite and you curve it around into a tube, you get a nanotube. Okay? If you take that shape and you put it around into almost like a little, what is it, a dodecahedron, I think? That's a buckyball. Okay, we have diamond, of course, which we've already looked at, and we have graphite. All right, so those are all very interesting allotropes of carbon. Do you need to know those? No. No. Okay. Now, what else do we have in here that is important? Let's try page 32. See if there's anything there we need to go over. 32. This is just a nice little summary. Ionic solids are held together by ionic bonds. Ionic bonds are strong, therefore the melting point is high, boiling point is high. They are hard. Molecular solids, this gives you a lovely picture because somebody else drew it, not me. This is C6H6 solid, which is benzene. Do you guys remember benzene? It's the hexagon shape. It's the one that had like this. And do you remember what was special about it other than the fact that it was in a ring? We had double and then single, double, single. So the bond order was 1.5, okay? But you could have any molecular solid. Intermolecular forces are weak, so the melting point is low, boiling point is low, and they are soft. Covalent network solids. The covalent bonds are strong. Melting point is high, boiling point is high, and they are hard. Metallic bonds are strong. Melting point is high, boiling point high. They are hard. Okay. Now, conductivity. Molecular solids, liquids, and aqueous solutions. So this could be like, a sugar water. So you can think about sugar. Does sugar conduct electricity? No. Do ionic solids conduct electricity? Solids. No. Why?
Because the ions aren't like they're stuck.
They have ions, but they're stuck in one spot, so they cannot move. Covalent network solids, can they conduct electricity? No, unless it is our favorite little exception to everything, which is graphite. Okay? Metallic solids, can they conduct?
Yes.
Yes. Aqueous ionic?
Yes.
Yes. Liquid ionic?
Yes.
Yes. And then graphite, of course, is our exception, which is yes. If you want to take a look at how they do it, metals conduct via their sea of electrons. Molecular things don't conduct because they hold on to their electrons. They're all stuck on their home atom. Molecules can be polar, but that just means they're going to align in an electric field. If my negative is over here, my positives are going to point towards the negative. And if my positive is over here, the negatives are going to point towards the positive, but they don't actually move because they're being pulled equally in both directions. Is good? Okay. Why is this sideways? Okay. Aqueous ionic, I think you guys know that one. Let's just skip over that. Covalent network solids. No. Here's a nice picture of the missing fourth bond in graphene.
Okay, is it?
This is page 37. There's the missing fourth bond in graphene. It's just sort of this balloon over top of the whole thing. This cloud. Okay? Cloud above and below. So this is delocalized pi bonds. Is good? Okay. I don't think we need to talk about anything else. Here is our brittleness of ionic solids. I put it in here because I promised you I'd give you a picture of it. Remember, when you hit it, it is brittle because negative ends up lining up with negative, positive ends up lining up with positive, and then they repel. Okay, and I think that's it. Yeah. Yeah. Would you like to review for the rest of the class?
Yes.
Okay, cool. Let's do that.